We're going to walk through a quick calculation of the thermal efficiency of an Otto cycle, and we're going to model the working fluid as ideal gas air. Now you may say that seems strange. A real internal combustion engine should contain a mixture of fuel and air, not to mention the fact that, strictly speaking, it's not a closed system, right? You actually have air and fuel come in, you have exhaust products go out. So how can we do this? And the answer is, that's part of the beauty of the Otto cycle. If you want something that you can actually calculate, anything remotely tractable for modeling an engine, you probably want to stick to this idealized cycle. Real combustion engine cycles are very complicated, and we don't want to get into all those details now. So we're cheating a little bit. We say it's ideal gas air, which is, of course, strictly speaking, not true. All right. So what are the conditions that we have to work with? Well, we're given all the temperatures. So we're given the initial temperature of 300 Kelvin. We go to 400 Kelvin from there, and I'm just going to write the hotter temperatures in red, obviously. There's no hard and fast rule for deciding what's hot and what's cold, but T3 is 900 Kelvin, T4 is 675 Kelvin. So if you're given this information and you need to draw out a TS plot, it would look something like this. So pretty steeply slanted. You notice that temperature 4 is greater than temperature 2, so the whole right end of that curve is up in the air. That's fine. And it's a power cycle. Okay, that all makes sense. Now the nice thing is, if we're dealing with ideal air gas, if we have the temperature, you can just look up the specific internal energy, and if you already watched the previous video tutorial, you know that the key for computing a thermal efficiency is just to know the specific internal energy. So actually, it's very straightforward. You look in the table in the back of your book, for example, look up the temperature, you get the internal energy immediately. So I'm just going to list those values here. U1, U2, U3, and U4. Now, these came out of your book. If you try to use the NIST website, you have a little trouble with Otto cycles because they use air. The NIST website doesn't break air apart from individual elements, so you would have to construct a bunch of models and combine them. That's way more pain than just looking in the back of your book, trust me. Okay, so let's compute the thermal efficiency. Eta is just 1 minus the quantity U4 minus U1 divided by U3 minus U2, and we have all four of those numbers. Let's plug them in. Okay, they're all in the same units, so that works out. Simplify a little, we get that it's 1 minus 0.717, so the efficiency comes out to be 28%, or 0.28. Now, one thing I wanted to illustrate with this example problem is that if we move this up, that's our thermal efficiency, and that is the correct quoted thermal efficiency for this Otto cycle. What you don't want to do, and what students sometimes try to do, is to try and calculate an efficiency for a complicated cycle with a bunch of different temperatures using the Carnot efficiency. And I warned about this in one of the worksheets in class, but you don't want to do this. So I'm going to misapply this intentionally. Do not do what I'm about to do, and you'll see why. We get a totally different answer that's wrong. So imagine we thought that because this was the Otto cycle, we could just apply eta max equals 1 minus Tc over Th. Now at this point, a student might wonder, well, we have 4 temperatures, how do you choose? And another bad decision would be to just take the coldest temperature as Tc and the hottest as Th. So if you do that, eta max is 1 minus 300 Kelvin over 900 Kelvin. So eta max comes out to be 0.67, not equal to 0.28. Not even close, off by more than a factor of 2. Don't do that. That's not right. The real way to get a thermal efficiency for something like an Otto cycle, a diesel cycle, or a Rankine cycle is to carefully apply the formula for its thermal efficiency and not to oversimplify by assuming you're only dealing with 2 temperatures.